When you think about it, you probably receive hundreds, even thousands of cues about what's going on in your environment every day, strictly from sound. In addition to things like speech and music, there are other bits of auditory information that shape your day: an ambulance passing by, a baby crying in the next room. And of course, sorry, just got a text. But there are a lot that we can learn, not just from what these cues mean, but from how sound itself works. Studying sound waves have helped doctors learn more about our ears and has allowed engineers to design things like microphones and speakers. Biologists have even used the science of sound to figure out how animals like elephants can communicate over long distances when we can't hear even them doing it. It all comes down to the fact that sound is a wave which travels through a media like air or water. And knowing that sound is a wave is important because it means that we can use the physics of sound waves to describe the quality of sound. When you think of a wave, you probably think of the kind you see at the ocean or the ones you made when you jump on the trampoline last time. Those waves produce ripples that run perpendicular to the direction that the wave is traveling in. But sound is the other kind of wave. It's longitudinal waves, meaning that the waves back and forth motion happen in the same direction in which the wave travels. Say you get a text message on your phone and it makes a nice bright little ding sound. What actually happened, like on a physical level? Your phone speaker contains a diaphragm, a piece of stirred material, usually in a shape of a cone. When you got the message, the electronics inside the speaker made the diaphragm move back and forth, which vibrated the air around your phone. That made the atoms and molecules in the air move back and forth. Then those moving particles vibrated the air around them, and as the process continued, the sound wave spread outward. Sorry, I'm just gonna turn it off. Anyway, physicists sometimes describe sound waves in terms of the movement of these particles in the air in what's known as a displacement wave. But by moving particles in the air, sound waves also doing something else. They cause the air to compress and expand, which is why sound waves are sometimes described as pressure waves. As the waves spread through the air, the particles end up bunching together in some places and spreading out in others. Together, all that bunching and spreading out cause airs of high pressure and low pressure to form and move through the air. It's useful to describe sound waves as pressure waves because we can build devices that detect those changes. That somehow the microphones works. For example, we use a diaphragm straight over a shield compartment, and as sound waves pass by, they create area of lower or higher the compartment. The difference in pressure causes the diaphragm to move back and forth, which electronics then translate into audio data. And the eardrums basically work the same way. As pressure waves pass through, they make the eardrum vibrate. The brain then interprets those vibrations as sound, but not all sounds are the same. Even when we know much about physics, humans were describing sound in terms mainly by things like loudness and pitch. Our understanding of those qualities have shaped the development of music, which we'll talk more about next time. But there's also a more physics side to those qualities of music. Pitch can be high or low, and it corresponds to the frequency. So air that's vibrating back and forth more times per second will have a higher pitch, and air that vibrating fewer times per second will have a lower pitch. Human hear sounds between when the vibrations are somewhere between 20 per second low end and 20,000 per second on the high end. As we get older and lose more cells that have a detect sound, the ability to hear higher pitched sounds. Some building security companies will take advantage of this, using devices that emit high-pitched noise that most people with SAA of 25 can't hear. The idea is that since kids and teens can hear it, it's super annoying to them. They won't hang out near the building, but some sounds are too high or low for any humans to hear. Sounds that are too high in pitch are called ultrasonic, and sounds that are too low are called infrasonic. Dog whistles, for example, gives an ultrasonic pitch that's too high for them, but is perfectly audible to dogs. Elephants, on the other hand, use infrasonic sounds to communicate with each other across long distances. They can hear the call from several kilometers away, but we can't hear them at all. Another aspect that shapes sound is its loudness. When you increase the intensity of a sound, you increase its loudness and vice versa. We have talked about the intensity of a wave before. It's the wave power over its area measured in watts per square meter. We have also said that the intensity of a wave is proportional to and the farther you are from the source of a wave, the lower its intensity, square of the distance between you and the source. And just as the range of pitches humans can hear, there's also a range of sound wave intensity that humans can comfortably hear. Generally, people can hear sounds from about 1 picometer up to 1 watt per square meter, which is about as loud as a rock concert. If the sound waves coming from a jet plane that's 30 meters away, and intensity of around 100 watts. Now I don't know if you are able to watch closer, but there's a reason people who work on the tarmac at the airport use these heavy-duty headphones. Below 1 picowatt per square meter, sounds are just too soft to detect them. And although we hear sounds above watts per square meter, they tend to hurt our ears. And here's one thing that about loudness and intensity is not a linear relationship. Generally, a sound wave needs to have 10 times the intensity to sound twice as loud to us. The relationship holds true as long as sound towards the middle of the range is with frequency we can hear. So instead of directly measuring the loudness of sounds by their intensity, we use the code decibel, which are based on Bell converts a sound wave's intensity to a logarithm scale. On the scale is 10 times higher than the previous one. The scale starts off with an intensity of 1 picowatt per square meter, corresponding to 0 bells. So a sound that 1 bell is 10 times as intense of a sound that at 1 bell, and a sound that 2 bells is 10 times as intense, but 100 times as intense as a sound is that 0 bells. Measuring and everything in bells can be kind of about sounds that are say 3.4 bells without having to deal with decimal points. That's why most of the time we will hear the loudness of sound described using the more familiar decibel unit, a tenth of bells. To find the loudness of a sound when you know its intensity, you take the base of its intensity, allow the reference intensity of 1 picowatt per square meter. Then you multiply that number by 10 to get the sound decibel level. We can use this equation to convert the intensity of that noisy rock concert was 110 per square meter. First, we take the base 10 log or 1 per square meter over 1 picowatt per square meter. Now 1 divided by 110 to 12 is just 110 to 12. So what we really want to do is take the base 10 logs of 110 to 12 or a trillion watts per square meter. What a logarithm asks you to do is find the power that you would need to in order to get the number in parentheses. In other words, we are looking for the exponent of 10 that would equal 1.10 to 12, which is just 12. To finish off the calculation of decibels from intensity, we multiply that value 12 by 10 to get the decibel level of the rock concert where they were standing 120 decibels out. You'll notice that as the sound of a wave moves closer to you, it gets louder, and it moves away, it gets softer. That makes sense. the closer you are to the source of the sound intensity of the waves. But have you ever noticed that the pitch of the sound changes too? It's called the dropper effect. And a sound of sound moves toward you, the pitch of the sound you hear increases. As the sound moves away, the pitch decreases. To see why, imagine you are standing on the sidewalk when suddenly you hear an ambulance siren stop. It's coming down from the road and it seems to be moving. The ambulance continues emitting sound waves at a certain frequency in the form of that silence. But as the ambulance moves toward you, the ambulance is also driving toward these sound waves. So the pitch that you hear at your eardrums are closer together, even though the same speed, and you hit by them more often, which means you hear a higher pitched sound. At the same time, it keeps emitting more sounds, which add more pitch to those early sounds. What you end up with is sound waves with a higher frequency than before. That's what hits your eardrum. So you hear a sound that are higher in pitch one you heard before the ambulance, and the ambulance passes you and start to drive away down the road, and the opposite happens. The sound waves are still coming toward you, but the ambulance is driving away from them. So the pitch that you hit the eardrums are farther apart, and here the dropper effect is unique to sound waves, so it's happen to light too, which means we can actually use it to measure the distance of stars. But more on that for now. You'll learn about the sound wave and how to move particles create differences in pressure. We also talk about pitch and how the intensity of sound waves changes with amplitude and distances. Finally, we discover the decibel as well as crash course physics is produced in association with BBC. You can hear over their channel to check out amazing shows like Raw Science, PBS Idea Channel, and It's Okay to Be Smart. This episode of Crash Course is filmed in Dr. Cherry with the help of these amazing people, and our equally amazing graphic team is Todd Cafes.